Okay, so good afternoon. Uh, so we will continue our discussion on this Bayesian decision-making process. And in the last class, we discussed about naive-Bayes classifier. Now, one of the limitations of naive-Bayes classification is that you are assuming that your attribute sets for a class, that likelihood of your attribute sets, they are conditionally independent. So within a class, uh, their likelihoods are independent. Now, this conditional dependency or independence can be better captured in a more generic form in a Bayesian network. So today, we'll discuss about the very brief overview of this network, properties of this network, and how inference is, uh, inference mechanism takes place under this network. So as you have already, as I mentioned, that it's a more general framework, and the conditional dependencies among the random variables, those are represented uh, in the form of a graph, in the form of a directed graph, in fact, directed acyclic graph. So there, in this graph, the nodes are representing the random variables, and the corresponding edges, they represent their relationships in terms of conditional dependencies. So as the example has been shown here, uh, uh, in this case, as you can see that this is an example of a Bayesian network in its simplest form. So you have two random variables, x and y. They are represented by these nodes. And this shows that uh, this arc shows that in this node, actually you are representing through this arc the conditional dependencies of y on x. Okay. So if you have multiple such input edges, you will have from different sources uh, random variables. They are, all of them are acting together to reflect the conditional dependencies on the random variable which is represented by the node, right? So this we'll see later on also in our subsequent slides. So what is important here, as you can see that in this node, we are associating an information which is called probability of x. So this information means what is the probability of occurrence of this random variable, or in terms of if I consider it's a variable, then you have its probability distribution also, that is also associated. On the other hand, for y, uh, we are representing the information, we are providing the information in terms of this conditional probabilities. So probability of y given x. So we are not giving the marginal probability. So the node which does not have any incoming edge showing the conditional dependencies on other variables. So those nodes are kind of free random variables in terms of this Bayesian network, and for them we have this kind of marginal probabilities. Whereas the nodes which are bound by these incoming edges, so there we are representing these conditional probabilities. So the Bayesian network, it involves representations where this is called topology. That means the structure of the graph, and also labeling of the nodes in terms of random variables. Finally, you should have also their probability distributions uh, in the nodes, at the nodes, so that you should have those information, so that finally you are representing the joint probability distribution of these two random variables. So given this information, like probability of x and probability of y given x, I can compute the joint probability of x and y. So that is why it is sufficient to represent in this form. So let me proceed further. So as I was mentioning, that this directed arc from x to y means that it is representing the influence of X on the occurrence of Y. So it's not a causal relationship, as I mentioned. So conditional probability does not mean that the X is a cause of Y. Don't take it like the way we can represent probability of Y given X. Similarly, we can represent also probability of X given Y. As you know that in the joint probability computations, uh, any of the marginal probability and the other conditional probability would be sufficient. And this is also a directed acyclic graph because there should not be any loop. So once you have describes the dependencies of probability of Y given X, there is no need of describing the opposite dependencies also. So that is not required, and it is sufficient to represent the joint distributions. So topology called structure, and this probability values, probability of X and probability of Y given X, or it may be a set of values because you know that depending upon the number of number of values of the random variable that can assume, this probability will the number of parameters will also vary. If it is a continuous case, then of course no, the probability distribution has to be represented in a different form. Like you should have some parametric representations. Enumeration for continuous random variable is not advisable. I mean, you have to discretize in any case in that case. But for discrete random variables, there are discrete finite set of values mostly, though it could be infinite also for a discrete set. But let us assume there are finite set of values. So you can represent the probability of X as a table for each discrete value of X. What is its probability? So that sum of all these probabilities finally becomes, that is equal to the. It depends upon the context, right? That would be equal to the 1 in that case. Similarly, probability of Y given X. There also you see that in this table it has to be a little elaborated. Like what are the values of Y, and for each value of X, you need to know its probabilities, right? So this is something you have to consider. So those are the parameters. So that can give you also the number of parameters that is required for a Bayesian network. So let me take an example to illustrate that fact. Say consider a simple Bayesian network like the previous one. Instead of X, I'm replacing it by a variable called rain. It's a Boolean variable. It means that whether it rains or not. So if R is true, that means it has rained. And if R is false, that means it did not rain. And the other one, the variable is called wet grass. And presentation is symbol is that. So wet grass is whether the grass is wet or not. So once again, it's a Boolean variable, right? So you can see that the grass could be wet even without rain, or with rain also there is a possibility that grass may not be wet also because of other environmental factor. So all the possibilities are there. So in terms of probability model, so I have this particular model in this case. Say we consider the probability of rain is 0.2, which means probability of not having rain is 0.8 in this case. So you have it is Boolean variable true. Whereas for wet grass, I'm not describing the probability of wet grass. Rather, what I'm describing here, I'll be describing because of this the presence of this age, entails that actually in this node, I have to describe the probability of W given R. That means the conditional probability of wet grass given rain. So that should be described, which means how many values are minimum value, how many values are sufficient, minimum values sufficient to describe the whole probabilities in this case. Anyone? Say how many probability values are required? What are the conditions?
Two,
So
sir.
you can see
The four,
yeah,
four.
4. Yes, but you can see there are redundancies. Like here, since I have represented probability of rain, I do not require to represent probability of not rain, because they are complementary. There are only two values. So if probability of rain is 0.2, probability of not rain is 0.8. That is implied. So I need only one value to represent this probability distribution of rain. Similarly, how many values are required? Other values could be inferred from them. See, if you know probability of wet grass given rain, it means also you know what is the probability of not wet grass given rain, right? If you know this value, the other value would be 1 minus probability of W given R. Similarly, but you need to know also what is the probability of wet grass when it does not rain. This is also this is not related with this. This is another event. If it is not rain, what is the probability of wet grass, right? So these two you require minimally. And other values, if you give, that would be a kind of redundant, but there has to be consistency once again. So that is what you see that in this Bayesian network, you require actually 3 parameters to describe. So in the topology, there are 2 nodes, 1 edge, but you require 3 parameters, right? So let me just proceed with this example. So as I was mentioning, so let me grab this annotation. See, this is the kind of parameters or independent parameters which are provided here. And other parameters are dependent on that. Other, like probability of not having rain or probability of not having wet grass if it rains, or not having wet grass if it does not rain. So this is the thing. So with this, can you work out, can you find out what is the joint probability distributions of rain and R and W? That means there are 4 combinations. What is the joint occurrences of rain and W, rain and wet grass, rain and not wet grass, not rain and wet grass, not rain and not wet grass, right? So please compute these things with this. So let me give you one example, like other things would be clear to you. Suppose I want to compute what is the probability of rain and W, right? So
yes,
what should be there? This?
the probability of R
Yes.
into
Yes.
probability of R given W. W given R.
Probability of R
into
right, and then
probability of W given R.
Yes, exactly. That's all. So what should be this value?
The 0.2 into 0.8.
0.16.
0.16. So similarly, please work out for the others. Like what is the probability of R and not W? What is this value?
The probability of R
0.04.
0.04, right? 0.2 into 0.2. So 0.2 and R
0.04.
Not W given R is 0.2. So 0.04, right? Similarly, the other two, what is the probability of not R W? Probability of
Same, sir. 0.04, sir.
same. You are saying not R W. Is it same? It should not be same, no? What is probability of not R?
Sir, 1 minus E first one.
That is 0.8, right? Probability of not R is 0.8 multiplied by probability of W given not R, which is 0.3.
Yes.
Sir. So 0.24.
0.2.
So it is 0.2. And then what is the probability of not R, not W, the other combination. What is the probability of not R, not W? What should be that value?
0.8 into
0.8 into 0.3.
0.7.
0.7.
0.56.
0.8 into 0.7, right?
56.
So that would be 0.56. Now you compute the marginal probability of W. What is the probability of W? What is the probability of W?
The probability of W
1 by 0.4, that is
Uh,
5 by
when
2,
you compute the marginal
2.5.
probability, you consider all the cases on which W can occur. That means you have to sum probability
first
of
one and third one.
probability of W given range, probability of W and R, and probability of W and not R, right? So this is 0.24, and I think this is 0.16. So it makes 0.4. So probability of W is 0.4, and probability of not W is naturally 0.6.
0.6.
Is this thing clear?
Yes, sir.
Yes, sir.
So you see that, no, just I have given you 3 parameters with this network, but no, you can infer about all other probabilities, including marginal probabilities, because you can have the whole distribution, joint distributions, complete joint distributions of these 2 random variables. So this is a very simple case. Now you think about a network which will have multiple nodes, more than 2 nodes, and they are all, of course, acyclic, directed acyclic graph, and they are representing, each edge is representing similar kind of conditional dependencies, and at each node you have this kind of probability tables, which are parameters. They are denoting the respective conditional dependencies, which are reflected by the connectivity of the edges to that node of different random variables. So that is what, and through which you can draw this kind of inference. So one of the interesting inference could be, say, I can say what is the probability of wet grass given rain. So if it rains, I can say what is the probability of a wet grass. From directly I can say, okay, it's very high probability, 0.8. But suppose I observe grass is wet, then what is the probability that it rained? That means I have to compute this probability of W given R, something like posterior, no? Something like posterior. So I can, this is forward inferencing and this is backward inferencing. So we call, this is a kind of, causal inference. Sorry, this is a diagnosis. This is a diagnosis and this is a causal. So I'll come to those terms. So can you compute this?
Yes,
What
sir.
is the, what is this probability?
The probability of R given W into probability of R divided by probability of W.
Yeah, so that same base theorem you can use. Probability of R, which is given here, into probability of
R given W.
Sorry, probability of R given, no, W given, oh, sorry, probability of
R given W.
So we have to find probability of R given
probability of
W.
W. Yeah. Probability of W into probability of R given
W.
divided by
Probability of R.
probability of R. All these values are available. Probability of W you have computed. You use it here, 0.4. Probability of R given W. Oh, sorry. Yeah. I should have the other one. I would like to compute this here. Right. So let us come to this. So I would like to go, find out. I said that if it is wet grass, then what is the probability that it rains? So which means I have to compute this. Probability of R given W. So there, as you are saying, that you have to write, probability of
R
W given R.
Given probability of, probability of R given probability of W given R
divided by probability of W.
divided by probability of W. So this you have to compute. Right. If you are computing this, I mean not this one, but this. So what is this value?
0.4.
This value would be, I think, 0.4. No? That means if it is wet, then the probability of rain is 0.4, and probability of not having rain is 0.6, which is higher. With this kind of probabilistic observations, you can see that when you see wet grass, that the probability of rain actually is lower than probability of not having. Anyway, so this is the kind of this kind of inference you can draw with this kind of model. So just let me summarize once again whatever I have computed. So I just mentioned that with this simple Bayesian network, we have these parameter sets. And as I mentioned that it is sufficient to specify the joint probability distributions. And this is a table of joint probability, so which we just computed. And as you can see also that the marginal probabilities of W can be computed from this table. Even the marginal probabilities of rain can be computed, which should be consistent with your given data. Then the inference mechanism, where so I just know, once again, I would like to stress that it does not mean any causality. But in the diagnostic inference, we find out what is the probability of W given R, which means it's a forward inference. So if it rains, what is the probability of W? Something like, if your diagnosis is true, what is the probability that you have the degree? Something like that. And so say, for example, in this case, it is quite high, 0.8. But on the other hand, the causal inference, that means if it is wet, then you are trying to find out that whether it rained or not, what is the probability. Then you can compute like this, and you can find that this value is 0.4, which is not very high, right? Rather, which is lower than the other event that it does not. It did not. Right. So knowing that the grass is wet, it increases probability of rain from 0. That is also another way of interpreting. So normally probability of rain is 0.2 marginal probability, but if you know the grass is wet, then the probability that it rains is higher. Now these are all these are all corroborating with our intuitions. So just to summarize once again, the Bayesian network, how this model is represented, it's a graph, and as I mentioned, you can have nodes corresponding to random variables and arcs between two nodes if they are not independent, conditionally independent, basically. So, so when they are independent, you know this result from statistics. You can say that probability of y given x equals probability of y, or even the other way, probability of x given y equal to probability of x. They are all equivalent statements. And when you got the joint probability distributions, then simply you can express it as the multiplication of these individual marginal probabilities. So these are certain things from from our basic knowledge of statistics itself, probability theory itself, we can infer. Now, the conditional independence means, in this case, so when we have said those independence of two random variables, there was no condition attached. Two random variables are independent, but conditional independence is that, so they are dependent on some random variable, and but if you consider that random variable, if you give you a value of that random variable, then these two random variable acts like an independent random variable. So that is the kind of conditional independence. So when you solve talked about Bayesian classifier also. There you have seen that we have used this property of conditional independence because within a class we said that probability distributions of attributes or probabilities of attributes there or attribute sets are probabilistically given. So one of the way um, theoretically you can write to this relationship of conditional independence, you can see that here we are considering two random variables x and y, and there is a third random variable z. And we're expressing that the, no, what is the conditional probability of joint occurrence of x and y given z. Now, we say that this is conditionally independent if this becomes true. That means this equals to the probability product of their conditional probabilities on z. It is the same. So there are other way of expressing this also. Like I can write also in the same form. In the previously also you have seen that how conditional, how the independence of random variables are expressed in terms of conditional probability. Here also that it means that the conditional probability of x given z does not depend on the occurrence of y. So that is what is expressed in this. They are all equivalent. So there are some from the topology point of view in a Bayesian structure. These are certain interesting properties which can be which we can directly obtain from the topology itself. Suppose you have a topology like this. Say z is conditionally dependent on y and x is conditionally dependent on z. Now, if I give you a value of z, if I observe z, given a z, then actually the occurrence of y and x, joint occurrence of y and x, they are conditional. So this is one example of kind of structure, head to tail structure connection. They said this topology. So if I consider also the joint probability distributions, you can also see that how joint probability of all these three variables are computed. Very simple. And that rule actually is applied throughout this network. If I give you a Bayesian network, joint probability computations of any subset of variables or any combination of variables, they can be done by by traversing to the nodes itself. So you can start with a marginal node with marginal probability. Then simply, if you go to the other node, you have to consider the joint probability means the probability of y multiplied by probability of z given y. So at this part. And then if you go there, simply you have probability of x given z. That's all. So you are multiplying these parameters only, following this up. And then you are getting joint probability distribution. Take another example, then it will be more clear. So this example. Say in this case, just tell me that what are the parameters you require to specify. You can tell me what are the parameters you require to specify, and here what are the parameters you require to specify. These three. First, you take this one. You will have probability of y. Okay? Assuming they are all binary variables. Yeah. That means they have only true and false value. So probability of y, and then you have probability of not y. So that is not required to specify. If you have probability of y, you have specified the other parameter also. Similarly, for here, you should specify what are the things like rain and wet grass. Here also you should specify what is the probability of
Z given Y
and
Z given not Y.
probability of
Z.
not given y. Right.
Yes.
That means all possible values of y you have to find. These are the only two values are there. So in the conditional table, you have only two, in this number of parameters only two. Similarly, since all are binary variables, what about how many you would like to have here?
the 4, but we have specified 2.
Pardon?
The 4.
4
There
you
are
are
total
saying?
4, but only we are specifying 2.
What 4? What are the things you would like to have here? Because you see that you require only this. Whatever combination, it is probability of not x, y, z. So here you have to just put not x. That's all. Here also you require only 2, no? Because it is only conditionally dependent on z. Given
Yes,
z,
sir. Yes.
it is not required to specify the conditional probability of y between x. Yes, there is a conditional dependencies between y and x also, but given z, they are independent. So you do not need to specify. You simply specify probability of here, like here, x given z and x given not z. Is it clear?
Yes, sir.
Here you have to specify x given z. So probability of this variable, random variable, for all different distinct values of z. So how many parameters now in this graph? How many parameters you have to specify for Bayesian network of 3 variables in this form, in this topology? What is the total number of?
5. 5.
8. Sorry, how many?
5.
5. Yes, you require 5. And but how many combinations are there in your joint probability distributions? If I want to express joint probability distribution, so how many rows you require in that table?
So
How
for
many
Z,
combinations?
it will be 4, and for X it will be 8.
That would be
8.
8.
And for Z it will be 4, and for Y it will be 2.
For Z it will be 4, and
Yes, sir.
for Y it will be 2.
Yes, sir.
So see, my questions is different. First thing is that number of parameters. I hope you have understood. My question is that if I want to get the joint probability distribution, which means for all different combinations, distinct combinations of x, y, z, I would like to have their probabilities. That is what is the joint probability distribution. So if we have the joint probability distribution, then I can compute any kind of marginal probabilities of any variables or even the probabilities of any combinations. So how many entries are there in that table?
Sir, 8.
There would be 8, isn't it? There would be 8. So you have 8 entries, but no, you require 5 parameters. So this is the kind of saving when you are effectively, your objective here is to represent this full probability distributions, joint probability distributions, considering the random variables. So that is your objective, and you should be able to compute the probabilities of any subset of these combinations, because in your inference mechanism, actually you'll be computing those probabilities, and accordingly, that would be used in your decision making process. But the Bayesian network gives you an efficient representation where you require less number of parameters. We'll also see, after we may not discuss much in this lecture, but no, you can read the advanced books or topics. There are computational algorithms to compute these kind of probabilities of any combinations efficiently using exploiting this graphical structure. There are a lot of redundancies in this computations. So there are some efficient algorithms by which you can compute those probabilities. Suppose I want to compute only, say, probability of x and y. Which means I need to, if I give you the joint probability distribution, it is trivial. So I would compute probability of x, y, z, probability of x, y, not z, because there are only 2 conditions, and then I will simply sum them. Right? So that would give me the probability of x, y. So if I consider that is a kind of marginal probability of these combinations, x and y. So if I give you the joint probability distributions, you can compute likewise any combinations of this set of random variables. But using the Bayesian structure, it is not required. So you can see that it is actually combinatorially explosive. So if I have 3 random variables, I have 2 to the power 3 combinations. If I have n random variables, I will have 2 to the power n combinations. So it is not advisable that no, I should derive the joint probability distributions using Bayesian network and then do all these computations. It would be no, computationally that would be inefficient and it would be exponential order. So there are methods by exploiting this topology and also this locality of your computations for certain computations of the conditional dependencies, you can reduce this computation. So we won't discuss much on this part, but no, I'm giving you, what are the motivations behind the representations and how they are used in the inference mechanism. Let us consider the other topology just for your better understanding. So in this topology, once again, you see that this is different than this one. Right? Here, x and y, they are both dependent on z, but x and y, given z, once again, they are not dependent like a head-to-tail connections. They are dependent in this fashion, which is, I think, there is a name. I'll come to that. Right. So, so in this case, how many parameters? Once again, how many parameters of z?
So one.
Only one, right? Probability of z only. What about this? How many parameters?
One.
Why one? Because
the probability
you
of
are
x
presenting
given
the
z.
conditional probability, no? X given
Yes,
z.
sir. Yes.
So you should have x given z and also x given not z. So you require 2. Similarly, here also you require 2.
2.
Probability of y given z and probability of y given not z. So here also you have 5 parameters. And since there are 3 variables, there will be 8 such combinations in that corresponding joint probability distribution table. Right. So this is called tail-to-tail connections. It was head-to-tail, and so you see that probability of x, y, z here in this case, the computation is quite direct. So probability of z multiplied by probability of x given z and probability of y given z. So you are basically multiplying all the probabilities, conditional probabilities expressed every node. Simply you are multiplying them, and you are getting the joint probability distribution of all the variables. So that is also another way of looking at the Bayesian network and its interpretation of its conditional independence. So this is what I just explained here. Right. So also the conditional independence can be expressed in this fashion. So just elaborating that part, when the value of z is known, it blocks the path from y to x, and if z is removed, there is no. So in other way, graphically, you can understand, if I remove the z and if random variables are not connected, then we can say they are conditionally independent based on that variable. It could be a combination of variables also. So a subset, if you remove that, a subset of a subgraph in your in the Bayesian graph, in the Bayesian network, and if you find all the random variables, remaining random variables, they are all disconnected, then all of them are conditionally independent on that set of variables. So that is one kind of interpretation. So from the topology, you can find out. So specific examples with those topology could be like this, just for your better understanding of giving some realistic examples. So you see that the sky is cloudy, and if it, what is the probability of rain if it is cloudy, and what is the probability of wet grass if it rains? So this kind of conditional dependencies can be captured using this kind of topology. On the other hand, if the sky is cloudy, what is the probability that sprinkler would be on? That means if the sky is cloudy, your expectation could be that no, you may not feel that your plants may not require much water because not much sun is there. There may be moisture in the soil. So there is a probability that if the sky is cloudy, that probability of sprinkler would be on or would be off. And similarly, there is a probability that it would rain or not. So given the sky is cloudy, then the probability of sprinkler and rain, these probability distributions, they are conditionally independent. So these are the same conditions. So I just mentioned those things I discussed in the previous slide, that when you perform the inference or diagnosis, that means forward inference or backward inference, there you see that you are playing with this kind of probability computations, and the structure and topology of the graph needs to be exploited there. So this is the computational problem. There is also another good example, just to give you a different flavor. We need to understand this would, I think, clear you some of your confusions. So in this case, you see that Z is a random variable which is conditionally dependent on X and Y, right? So how the parameters would be specified here in this case? What you would specify here?
So probability of Z given X naught, Y naught.
Probability of
Z given not X, not Y.
not X, not Y.
Similarly, probability of Z.
Yes. So as you see that when you are setting the conditional probability, someone's microphone is maybe you are answering, that's why. Anyway, so all possible combinations, all possible values of these combinations that you need to consider. All possible combinations that you need to consider and specify the corresponding conditional probabilities. Right? Because if you specify that, you are also specifying probability of not Z given not X not Y. So only one is sufficient. So how many values you need to specify here for a binary variables, random variables? All of them are binary.
So for Z, it will be 4.
How many?
So 4.
It's 4, right? And how many parameters here?
So 6.
Total 6. In this case, this node you require just one. In this node, you require just one because these are all marginal probabilities. So in this topology, you require 6 instead of 5, right? In the previous top. So number of parameters, that is the requirement of that number of parameters for specifying a network, it depends upon the topology. Though you have number of random variables is same, that means if I consider the joint probability distribution, till I have only 8 combinations to specify. But here you require more number of parameters because of these particular connections. And your inference also goes following the same structure. So you see that this is how joint probability of X, Y, Z is computed. Simply you are multiplying the individual probabilities, that marginal probabilities of nodes, and then conditional probabilities at that node. So probability of X, probability of Y, then probability of Z given X, Y. So that is what you got to do. And probability of X and Y, note that they are independent in this case. So this is another thing you should consider, that X and Y is not conditionally independent on Z, right? That you should know. So given Z, they are not conditionally independent, though they are independent without Z, specification of Z. So these are certain basic fundamental or brief outline of Bayesian networks. Um, if you consider a large network, they can be similarly you can have large network by using simpler graphs. And so this is one. It's not very large, but a bit more. I should say complex network. With this structure, we have four variables, four random variables, and here you can have already mentioned how many parameters are required at each node. I hope you have understood that, because at every conditional dependencies, you should find out what are the possible combinations of your input variables for which the probabilities are to be specified for that variable. So that is what is you have to find out, and then you can get that number. So in this case, you have actually nine parameters, and how many combinations are possible with these four variables? 16, right? So this kind of savings are required. So for a large network, savings are significant. For a large network, savings are significant. And no, these are certain advantages. First, explicitly it encodes in dependencies, and then you can compute locally. So you can compute locally, and then you can aggregate them. So there are algorithms. Unless you go through the algorithms, it will not be very clear to you. And usually the problems are that sometimes we provide you like the cause of the causal inference example. So if it rains, then if grass is white, then what is the probability of rain? So grass is white is a kind of evidence node, right? And your query node is your rain. Similarly, given a network, you can have a set of evidence nodes and set of query nodes. So your inference mechanism is that if I give you a set of evidence nodes, what is the probability of my combinations of those query nodes? So this is the basic computations that we carry out in Bayesian network. It says that given the value of any set of variables as an evidence, infer the probabilities of any other set of variables. So this computation is done. And as you can see that no, it is nothing but a probabilistic database. So all these parameters are specifying you a probabilities are specified to get you the probabilities of different combinations. And the difference between unsupervised and. So this is another thing, because you do not have the complete knowledge, you have partial knowledge. So you cannot say it's a kind of supervised approach always. So inference through Bayesian network, I just mentioned how the joint probabilities are computed for any combinations of variables. This is how it is computed. And as I said, that you can marginalize it, but no exponential number of joint probability combinations. So it's not exploiting the implied independencies. So, and there are a lot of redundancies in the computations. So there are efficient computations through belief propagation. So there is a computation called belief propagations approach, by which you can compute these probabilities, which can accommodate also hidden variables. Just before I end today's stop today, just to note, to draw your attention to this fact is that naive-based classifier is also a special case of Bayesian network. So here you can see that every class is having a probability, marginal probability, and all other attributes, variables, random variables, they are conditionally dependent on this class only, and they are all conditionally independent among themselves. So in this way, you can compute the joint probabilities, and that you can apply for computing the posterior also. Okay, so with this, let me stop today, and I can take a few more questions today if you have. So any question from your end? Fine. So in that case, we'll meet tomorrow at 8 a.m. Okay. Thanks.
I have not a question, but I have a request that may you extend the deadline of assignment submission by a few days?